natural or parameter. Links here. For the usage of this term in differential geometry, see differential geometry of curves. In probability and statistics, an exponential family is a set of probability distributions of a certain form, specified below. This special form is chosen for mathematical convenience, on account of some useful algebraic properties, as well as for generality. As exponential families are in a sense very natural sets of distributions to consider, the concept of exponential families is credited to E. J. G. Pittman, Darmois, and B. O. Koopman in 1935-36. The term exponential class is sometimes used in place of exponential family. The exponential families include many of the most common distributions, including the normal, exponential, gamma, chi-squared, beta, Dirichlet, Bernoulli, categorical, Poisson, Wishart, inverse Wishart, and many others. A number of common distributions are exponential families only when certain parameters are considered fixed and known, e.g., binomial, multinomial, and negative binomial. Examples of common distributions that are not exponential families are students T, most mixture distributions, and even the family of uniform distributions with unknown bounds. See the section below on examples for more discussion. Consideration of exponential family distributions provides a general framework for selecting a possible alternative parameterization of the distribution, in terms of natural parameters, and for defining useful sample statistics, called the natural sufficient statistics of the family. For more information, see below. Definition. The following is a sequence of increasingly more general definitions of an exponential family. A casual reader may wish to restrict attention to the first and simplest definition, which corresponds to a single parameter family of discrete or continuous probability distributions. Scalar parameter. A single parameter exponential family is a set of probability distributions whose probability density function can be expressed in the form where t, h, eta, and a are known functions. An alternative, equivalent form often given is or equivalently the value theta is called the parameter of the family. Note that x is often a vector of measurements, in which case t may be a function from the space of possible values of x to the real numbers. More generally, eta and t can each be vector-valued such that is real-valued. If eta equals theta, then the exponential family is said to be in canonical form. By defining a transformed parameter eta equals eta, it is always possible to convert an exponential family to canonical form. The canonical form is non-unique, since eta can be multiplied by any non-zero constant, provided that t is multiplied by that constant's reciprocal, or a constant c can be added to eta and h multiplied by to offset it. Even when x is a scalar, and there is only a single parameter, the functions eta and t can still be vectors, as described below. Note also that the function a or equivalently g is automatically determined once the other functions have been chosen, and assumes a form that causes the distribution to be normalized. Furthermore, both of these functions can always be written as functions of eta, even when eta is not a one-to-one function, i.e., two or more different values of theta map to the same value of eta, and hence eta cannot be inverted. In such a case, all values of theta mapping to the same eta will also have the same value for a and g. Further down the page is the example of a normal distribution with unknown mean and known variance. Factorization of the variables involved. What is important to note, and what characterizes all exponential family variants, is that the parameter and the observation variable must factorize, either directly or within either part of an exponentiation operation. Generally, this means that all of the factors constituting the density or mass function must be of one of the following forms, where f and h are arbitrary functions of x, g and j are arbitrary functions of theta, and c is an arbitrary constant expression. There are further restrictions on how many such factors can occur. For example, the two expressions are the same, i.e., a product of two allowed factors. However, when rewritten into the factorized form, it can be seen that it cannot be expressed in the required form. To see why an expression of the form qualifies, note that and hence factorizes inside of the exponent. Similarly, and again factorizes inside of the exponent. Note also that a factor consisting of a sum where both types of variables are involved cannot be factorized in this fashion. This is why, for example, the Cauchy distribution and student's t distribution are not exponential families. Vector parameter. The definition in terms of one real number parameter can be extended to one real vector parameter. A family of distributions is said to belong to a vector exponential family if the probability density function can be written as or in a more compact form. This form writes the sum as a dot product of vector-valued functions, and an alternative, equivalent form often seen as in the scalar-valued case. The exponential family is said to be in canonical form if a vector exponential family is said to be curved if the dimension of is less than the dimension of the vector, that is, if the dimension of the parameter vector is less than the number of functions of the parameter vector in the above representation of the probability density function. Note that most common distributions in the exponential family are not curved, and many algorithms designed to work with any member of the exponential family implicitly or explicitly assume that the distribution is not curved. Note that, as in the above case of a scalar-valued parameter, the function or equivalently is automatically determined once the other functions have been chosen, so that the entire distribution is normalized. In addition, as above, both of these functions can always be written as functions of, regardless of the form of the transformation that generates from. Hence an exponential family in its natural form looks like, or equivalently note that the above forms may sometimes be seen within place of. These are exactly equivalent formulations, merely using different notation for the dot product. Further down the page is the example of a normal distribution with unknown mean and variance. Vector parameter. Vector variable. The vector parameter form over a single scalar-valued random variable can be trivially expanded to cover a joint distribution over a vector of random variables. The resulting distribution is simply the same as the above distribution for a scalar-valued random variable with each occurrence of the scalar x replaced by the vector. Note that the dimension k of the random variable need not match the dimension d of the parameter vector, nor the dimension s of the natural parameter and sufficient statistic t. The distribution in this case is written as or more compactly as or alternatively as measure-theoretic formulation. We use cumulative distribution functions in order to encompass both discrete and continuous distributions. Suppose h is a non-decreasing function of a real variable. Then Lebesgue-Stieltjes integrals with respect to dh are integrals with respect to the reference measure of the exponential family generated by h. H is a Lebesgue-Stieltjes integrator for the reference measure. When the reference measure is finite, it can be normalized, and h is actually the cumulative distribution function of a probability distribution. If f is absolutely continuous with a density, then so is h, which can then be written dh equals h dx. If f is discrete, then h is a step function. Interpretation. In the definitions above, the functions t, eta and a were apparently arbitrarily defined. However, these functions play a significant role in the resulting probability distribution. T is a sufficient statistic of the distribution. For exponential families, the sufficient statistic is a function of the data that fully summarizes the data x within the density function. This means that, for any data sets x and y, the density value is the same if t equals t. This is true even if x and y are quite different, that is, The dimension of T equals the number of parameters of theta and encompasses all of the information regarding the data related to the parameter theta. The sufficiency statistic of a set of independent, identically distributed data observations is simply the sum of individual sufficiency statistics, and encapsulates all the information needed to describe the posterior distribution of the parameters, given the data. This important property is further discussed below. Eta is called the natural parameter. The set of values of eta for which the function is finite is called the natural parameter space. It can be shown that the natural parameter space is always convex. A is called the log partition function because it is the logarithm of a normalization factor, without which would not be a probability distribution. The function A is important in its own right, because the mean, variance and other moments of the sufficiency statistic T can be derived simply by differentiating A. For example, because lane is one of the components of the sufficiency statistic of the gamma distribution, can be easily determined for this distribution using A. Technically, this is true because is the cumulant generating function of the sufficiency statistic. Properties. Exponential families have a large number of properties that make them extremely useful for statistical analysis. In many cases, it can be shown that, except in a few exceptional cases, only exponential families have these properties. Examples. Exponential families have sufficient statistics that can summarize arbitrary amounts of independent, identically distributed data using a fixed number of values. Exponential families have conjugate priors, an important property in Bayesian statistics. The posterior predictive distribution of an exponential family random variable with a conjugate prior can always be written in closed form. Note that these distributions are often not themselves exponential families. Common examples of non-exponential families arising from exponential ones are the student's t-distribution, beta binomial distribution and Dirichlet multinomial distribution. In the mean field approximation in variational Bayes, the best approximating posterior distribution of an exponential family node with a conjugate prior is in the same family as the node. Examples. It is critical, when considering the examples in this section, to remember the discussion above about what it means to say that a distribution is an exponential family, and in particular to keep in mind that the set of parameters that are allowed to vary is critical in determining whether a distribution is or is not an exponential family. The normal, exponential, log normal, gamma, chi-squared, beta, Dirichlet, Bernoulli, categorical, Poisson, geometric, inverse Gaussian, von Mises and von Mises-Fisher distributions are all exponential families. Some distributions are exponential families only if some of the parameters are held fixed. The family of Pareto distributions with a fixed minimum bound xm form an exponential family. The families of binomial and multinomial distributions with fixed number of trials n but unknown probability parameter are exponential families. The family of negative binomial distributions with fixed number of failures R is an exponential family. However, when any of the above-mentioned fixed parameters are allowed to vary, the resulting family is not an exponential family. As mentioned above, as a general rule, the support of an exponential family must remain the same across all parameter settings in the family. This is why the above cases are not exponential families. In all of the cases, the parameter in question affects the support. For similar reasons, neither the discrete uniform distribution nor continuous uniform distribution are exponential families regardless of whether one of the bounds is held fixed. The Weibull distribution with fixed shape parameter k is an exponential family. Unlike in the previous examples, The shape parameter does not affect the support. The fact that allowing it to vary makes the variable non-exponential is due rather to the particular form of the variable's probability density function. In general, distributions that result from a finite or infinite mixture of other distributions, e.g., mixture model densities and compound probability distributions, are not exponential families. Examples are typical Gaussian mixture models as well as many heavy-tailed distributions that result from compounding a distribution with a prior distribution over one of its parameters, e.g., the student's t-distribution, and the beta binomial and Dirichlet multinomial distributions. Other examples of distributions that are not exponential families are the F-distribution, Cauchy distribution, hypergeometric distribution and logistic distribution. Following are some detailed examples of the representation of some useful distribution as exponential families. Normal distribution, unknown mean, known variance as a first example. Consider a random variable distributed normally with unknown mean mu and known variance sigma 2. The probability density function is then this is a single parameter exponential family, as can be seen by setting if sigma equals 1 this is in canonical form, as then eta equals mu. Normal distribution, unknown mean and unknown variance. Next, consider the case of a normal distribution with unknown mean and unknown variance. The probability density function is then this is an exponential family which can be written in canonical form by defining binomial distribution as an example of a discrete exponential family. Consider the binomial distribution with known number of trials n. The probability mass function for this distribution as this can equivalently be written as which shows that the binomial distribution is an exponential family, whose natural parameter is this function of p is known as logit. Table of distributions. The following table shows how to rewrite a number of common distributions as exponential family distributions with natural parameters. Refer to the flashcards for main exponential families. For a scalar variable and scalar parameter, the form is as follows. For a scalar variable and vector parameter. For a vector variable and vector parameter, the above formulas choose the functional form of the exponential family with a log partition function. The reason for this is so that the moments of the sufficient statistics can be calculated easily, simply by differentiating this function. Alternative forms involve either parameterizing this function in terms of the normal parameter instead of the natural parameter, and/or using a factor outside of the exponential. The relation between the latter and the former is to convert between the representations involving the two types of parameter. Use the formulas below for writing one type of parameter in terms of the other. The three variants of the categorical distribution and multinomial distribution are due to the fact that the parameters are constrained, such that thus, there are only k-1 independent parameters. Variant 1 uses k natural parameters with a simple relation between the standard and natural parameters. However, only k-1 of the natural parameters are independent, and the set of k natural parameters is non-identifiable. The constraint on the usual parameters translates to a similar constraint on the natural parameters. Variant 2 demonstrates the fact that the entire set of natural parameters is non-identifiable. Adding any constant value to the natural parameters has no effect on the resulting distribution. However, by using the constraint on the natural parameters, the formula for the normal parameters in terms of the natural parameters can be written in a way that is independent on the constant that is added. Variant 3 shows how to make the parameters identifiable in a convenient way by setting this effectively pivots around pk and causes the last natural parameter to have the constant value of 0. All the remaining formulas are written in a way that does not access pk, so that effectively the model has only k-1 parameters, both of the usual and natural kind. Note also that variance 1 and 2 are not actually standard exponential families at all. Rather, they are curved exponential families, i.e., there are k-1 independent parameters embedded in a k-dimensional parameter space. Many of the standard results for exponential families do not apply to curved exponential families. An example is the log partition function a, which has the value of 0 in the curved cases. In standard exponential families, the derivatives of this function correspond to the moments of the sufficient statistics, e.g., the mean and variance. However, a value of 0 suggests that the mean and variance of all the sufficient statistics are uniformly 0, whereas in fact the mean of the ith sufficient statistic should be pi.